Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video is going to take a look at x86 assembly language, and we're going to start with an advanced procedure review, basically kind of taking the last lecture and going with it a little bit more, doing a couple more review problems, and then pushing off into the final topic of our coursework, recursion. So I'm just going to start out with a bunch of your turns. So I think I have 5 of them here. So the first one here, I would like to create a function, do all the hard work of creating a function that's called print hello, that would take no parameters, print the words hello everyone, or just hello something, to the screen, and then return back and return nothing. So that is the main function that I would like to be able to call, and I have that listed here. You can already see the code, but that's just in the next slide, so it's not like it's a secret or anything. So then in the next slide, this is how I would go about setting all of that up. I need a data segment. It needs to be a global string. And so hello byte, hello everyone, and comma 0, make sure that null terminator is there. And so just say like, that's great, we have our data, and I don't need to pass that in or anything because I'm just going to directly use it inside of the procedure. And we know, according to the Irvine library, we have to set the EDX register with the offset of the string I want to print, and then I can call write string. So that's perfectly fine. And then with my ret, since nothing is pushed onto the stack, I don't need a ret 4, ret 8, or anything like that. But then it comes down to, again, our contract is when I call a function and I return back all of the registers, in this case, since it's a void function, it doesn't return anything, every register has to be put back to what it was previously. And so since I changed the EDX register here, I need a push and a pop to make it work. I mean, so that's very basic stuff here, and there is my hello everyone function, and there it is screaming out hello everyone. And so this is, once you have this, like this works perfectly every time. Okay, so that's example 1. So example 1 there was not very extensible. It basically just printed out one string of one string only. So what if we tried to do pretty much the exact same thing, but this time around I'll pass in a string to do all the hard work. And so this, instead of just being hello everyone, I can make that string anything as long as I pass that pointer in. So so in the main, this time around, I'd like to push the offset of some pointer to some string variable or some string array, character array, and then I will call this print text function to do all the hard work, just like I could do, you know, this is a 2-liner. If I were using the Irvine library, again, I would just move the pointer into the EDX register and call the print function. But now we're going to do things the more correct way using the past parameters and all these kind of details. So this thing will print April 28th. And here I was being smart about this, and this is April 28th. It was yesterday when I made this, so today's today. So it will print out April 28th, 2020. And yours, it will print out April 27th, 2020, if you go to look at the PowerPoint slide at any other time. So again, here is my text, here is my string, here is my call to this, and then here is the work to get everything done. So there's one parameter passed into the function. So the rule is if there's a parameter passed in, I need these first 2 lines up front to get the EBP register all set up and modified, so I can set up my call stack. And so I do a push EBP, and then I move EBP comma ESP. That's always the same code, always up front, and it's always when I have parameters passed in. And then since I push it here, I do a pop. And then right after it, I set up a return 4, and the return 4 is because this time around I'm pushing a parameter onto the stack, so it's the function's responsibility to pop it off the stack when it's all said and done. So ret 4 does the job. Okay, so that's kind of like the bread part of the sandwich there, and then now everything else is it's all of this for 2 lines of code, as I was explaining, right? So from dword pointer EBP plus 8, because that's always where basically the last parameter pushed onto the stack prior to the function call. That's the memory address. Is if we set everything up rightly, it'll always be EBP plus 8. So as long as I take that, and I say always treat it like a double word, because everything we push onto the stack is going to be 32 bits, 4 bytes. Treat it like a double word, put it into the EDX register because it's already coming in as an offset. It's already a pointer, so I just have to basically jam it into EDX before I call write string. And just like the previous example as well, the EDX register is modified and we want to make sure we put that back. So before I do this, like it's, we'll see there's actually 3 layers of push pop operations. The first layer is this one for the parameter passing. The second one we'll see later in the 5th example is local variables. And then the third one here is what did the actual the actual work of the function, what did that modify? And then that goes in the 3rd slot. So here I push EDX before I use it, and then I pop it back before I do everything else. So notice, since I'm using 2 layers of pushes, I have to make sure I pop everything back in reverse order. So I have to make sure I pop the EDX first to make up for the push EDX, and then I have to pop the EBP to make up for the push, and then I do the return. So it's more work, but it's it's 8 lines of code for 2 lines of work. But computers do this all the time when it comes to threads and thrashing and all sorts of kind of stuff going on here. So this isn't, as much as it's 8 lines of code to do 2 lines of code, we never have to write this ever again, and it works perfectly in every case. And it works for anything I would ever push into it, because I can pick any string. As long as it's a null terminated string, I can go ahead and make it work. So that's good for number 2. Moving on to number 3. So this function I'm setting up to do basically just multiply, because we've discussed in previous chapters that multiply and divide are a little different. They require a little bit more work, but like everything else, if I could do it one time, and set this thing up, maybe it's a tiny bit slower, but I never have to think about it ever again. All I have to do is push 2 values onto the stack, call multiply, and the EAX register will magically hold the result when I get back. I love this idea. So here is the idea: push 105, push 22. I should get 2310 on the back end after I call multiply, and I come back and I call write int, and you can see that I do, because here's my 2310. So, okay, so moving forward, how do I write some code for this? And so again, I have 2 parameters I pushed in this time. So I need my push, my move, my pop, and my ret. And again, the ret, it's always 4 times the number of parameters you've passed in, because it's always 4 bytes per parameter. So there's 2 parameters, 2 arguments. 4 times 2 is 8. I need a ret 8 here. So that covers the first 2 and the last 2. And so now, again, the hard work of this is the next step. These pushes and pops that I'm going to talk about after I'm done, those always occur last. Like we put the push and the pop in here for the EBP stuff. If we use local variables, we put that in as well. But everything else here, the 3rd layer, that occurs after I get my function done, because there's no way you're going to know what you're going to do until you're done doing it, and then you can kind of bring it back, clean it up, and then go, well, what do I need to fix up to clean up so that when I return back, everything's put back to how it is. So there's no reason to do that stuff until you're all done. And multiplication is very simple. I just have to take one of the 2 variables out of memory, and I'll just go to EBB plus 8, it doesn't matter which one in this case, and I'll move it over into the EAX register, because EAX is the register I need to push something into, put value into to do a multiplication, and then I can call an imul on the, using the other operand, which is sitting in RAM, as the other part of the, the value that I'm multiplying together. So this is EBP plus 8 times EBP plus 12, and then EAX will hold the part we care about, the 32-bit low end of the result. And remember then, because of the way this multiplication works, EDX is also blown out as well, because if there was a 64-bit quantity, if there's anything in there, an overflow, the EDX register would hold that. And so, and I don't care necessarily, because that we don't, in 32-bit math, we do this in C++, Java, you name the language. If you overflow, it doesn't magically keep that extra stuff, it just overflows. So we're not going to worry about it, just like the same in assembly language, in this function anyway, like we don't care, just like we wouldn't in C++. So because the EDX register is blown out, I have to push it, and then I have to pop it. And again, it's all in reverse order. I push it here, it's a push, move, push, 2 pushes. So I got to do pop EDX, a pop EBP, and then a ret 8. And everything goes on the stack and everything unwinds as I was expecting it to. So that's a good example. And you could take this example, because this will be great for your finals, so you don't have to think about multiplication or anything. You could take what you see here and apply it to division and modulus operations. Then you don't have to think anymore. You can just set everything up like you see back in the main here. and you can just not worry about it anymore and just test it out before test it before you put it out in production. But once you know it's working very well, you have a library function you can use forevermore. So now we're going to look at a little more complicated kind of stuff here. Example 4 is a step up, and example 5 is definitely a step or two up here, just to kind of put everything together now. So I have a function here called change, and so now the difference is pretty much everything that I've given examples for up to now has used pass by value when it comes to all the parameters. But now you can see here I'm using in C++, I'm using a pass by reference for the B. And so that's a huge difference. Remember back to previous lectures, what the difference is. Pass by value, I like to use like a Xerox copy machine example, where it's like if I have if I'm X, I have a variable in my hand. If I'm passing by value, I'm going to the copy machine, I'm making a copy, and I have 2 copies in my hand. The master is mine, and I give you on the other end of this thing a copy of my data, so you can go ahead and change it however you see fit. You can rip it up or never use it, or I don't care. It doesn't matter to me. Like whatever happens on your end doesn't affect me in the slightest bit. So that means whatever I change inside of here, it affects your copy, but it doesn't affect mine. And so that is in complete 180 to what a reference is. And when we're talking about pass by reference, I'm passing a memory address to where the real data is. So it's basically considered I'm handing you my master copy with the promise that when you're done with it, you'll give it back to me, because we're both basically sharing that same piece of paper. And so that's why in C++ you'll see a lot of people put const in front of these things just as a reminder, like I'm not allowed to touch it. Basically, I'll hold it up for you, you can read off of it, but if you go to touch it, I'll slap your hand away and say, nope, you're not allowed to. But in assembly language, there is no idea of const, because that's all just a high-level representation of things. So basically, I'm putting the thing in front of you or handing you the copy, and then you could change it. Like in this case, I am changing it, and so it affects your copy and my copy because they're the same copy. So this program is just to show that we can represent the same idea in assembly language. It just takes more work, and so you can see there's a lot more code over here on my end here, but I can show you, indubitably here that it does work. Oops, whoa, what the heck was that? Okay, so the main, there's a lot going on here, but it's just a lot of repeated code. So basically that cout statement, cout an A, cout, and then a B, and then cout an N line, there's just a lot of code there. And I'm sorry, cout X, cout Y, cout N line. That is all this here. There are 1, 2, 3, 4, 5, 6, 7 lines to do 1 line of C++ code. And so then it's just repeated down here below because it's the same exact line. But in the middle here, that is the call to the function, push X onto the stack, push the offset of Y onto the stack, and then call change. And so because when I'm passing by value, if I push a value onto the stack, that's just a value. X is a 5. I'm pushing a 5 onto the stack. But if I push offset of Y onto the stack, I'm not pushing the 6 onto the stack, I'm pushing the memory location of where Y is stored. So it's a huge difference. And in this case, if you want to think of it, you actually kind of get a 4 out of this. Like, how do I get 4? And because of the way the offsets work in assembly language, remember how the data segment starts off with X being at memory location 0 when it comes to the data segment, and since it's 4 bytes large, Y would be at location 4. So it's one of those weird things. It actually passed a 4 along in this case, but that's not the point here. The point is it's passing the memory address of where Y is stored, because that's what a reference is, and that's why references and pointers are essentially, let's not get into the details, but are essentially the same exact detail. They're the exact same thing. It's just a reference holds the same syntax as a value type, but a pointer has the different syntax with the dereference operators and arrow operators and all sorts of stuff, depending on how complex you go with that pointer stuff. So this is the main function for this activity. And so the idea of now the same thing with the change function, oops, going the other way here. And now you can see that, a little complicated here. Oh yeah, I'm sorry, and also setting up the variables, because integers are signed double words in our environment. So X signed double word 5, Y signed double word 6, and now it's just a matter of fixing up the change function. And it's interesting, right? Because like before, it's 3 lines of C++ code, but it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15 or 16 lines of assembly language. Isn't that the fun stuff of assembly language? But that's how it works, right? So this is the exact same thing. It's 7 lines of code or whatever it is to print out A, print out B. But the difference in it is, of course, that we're using the EBPs, right? We're using EBP plus 8, EBP plus 12 for these parameters. And so it just gets a little tricky because as you're doing this, and I didn't transfer this, you'll see in the next example that I actually kind of revise and modify and massage down the C++ code that I've written so that it's easier for me to translate. But in this case, since I'm going and I'm pushing the X onto the stack first and the Y onto the stack second, the EBP plus 8 is actually going to be the B, or the Y in this case is going to be B. So that's plus 12, I'm sorry, plus 8, and then the A variable here is going to be the plus 12 because it's going to be the second, it was pushed on the stack first, which means it's further away from the base EBP because of the way the stack is being built. So that's what I'm saying here, like if I'm taking A and I'm going to set it equal to 10, well, A is actually stored at EBP plus 12, again for the same reason. EBP plus 8 is going to be B, but EBP plus 12 is going to be A. So I'm just moving 12 into that location. And now this is the tricky part, because you can't just say put 14 into EBP plus 8, because again, now this is a reference type. So this is because in that memory location, or I'm sorry, in that memory location is a memory address. So it's like it's a two-layer thing here. It's not just a value stored under the hood that I'll just change it to 10. And you could theoretically change it to 14, but then you're not changing the pointer, you're changing a value, and you're basically just disobeying the whole rules of what a reference is. And so you're really not doing reference types. You're basically just overwriting and just going, nope, I don't want to do a reference. I'm just going to treat it by value. And you're not going to really get the result that you're supposed to be getting out of this. So what I can do here, it's a two-step process then, is I move the value into the EAX register of the pointer. So now the pointer is now stored in the EAX register. And then what I can say is, hey, dereference. Remember the star, star, A, star, this, that, when it comes to the way a pointer syntax is in C++. And so I can say, okay, I know I have a memory address stored in the EAX register, but why don't you go to that memory address and put the 14 in wherever that memory location actually is. And that's what the idea of dereferencing is. So 14, whatever EAX is pointing to, which is the Y variable sitting in the global variable section, in the data section, the data segment, put a 14 in there. And so huge difference, right? I mean, is it like this was real easy and this was a huge talking, there's a huge amount of talking to get us to the end goal of what did I just do? And then I can go ahead and print out all of this information just like I did before, just using the EBP pluses instead of the global variables to print everything out like in the previous section. So like, yeah, X's and Y's in main, but EBPs, pluses, plus 8s, and plus 12s here in the change function. So you put that all together, and what is my end result? So I get, you can look at this here, I get a 5, 6, 10, 14, 5, 14, and of course, the first thing you ever ask is this correct? And yes, the answer is yes, this is a correct thing. And so the first line of printing, coming back to the main function here, was just printing out the unmodified values. So 5 and 6 would be printed out, 5 for X, 6 for Y. Fair enough. And so the second part inside of the function is this guy, the change function. I'm printing out, after I've modified the values from 5 and 6 to 10 and 14, print them out. So it makes sense again that in this case, a copy of X is sitting on the stack, and then I change that to 10, and then I changed whatever Y is, since it's a reference, I changed that to 14, so you can see that it is 14, so 10 and 14 printed out. So now, coming back from this, coming back from the change function back to main and printing everything out, X and Y again, you can see where we're at. Now it's half and half. So now when I passed by value, yes, I modified the copy, but when I came back to main, the original X variable has not been modified. It came back and now I'm printing out 5 again. But for the Y, which was passed by reference, which was passing the master copy, which was modified by the function, I come back and it prints the 14. And so this is perfectly correct. That's the whole difference between passing by value, passing by reference / pointer. Okay, the final example I'm going to look at before we move on to recursion here is the idea of a Fibonacci sequence. And we should all, as computer scientists, Fibonacci factorials and a few other things, we love these things because they're very good examples for just like loops and loop structures and recursion and these kind of things. So when I start with the Fibonacci sequence, the 0th number is a 0. The first number is element number 1 in the list is a 1, and everything from there can be determined by just saying, okay, if I want in this case, I'm going to want the 19th Fibonacci number, and so it's just going to be equivalent to the 7, if I know what the 17th number is, I can add it to whatever the 18th number is, and I can figure out what the 19th number is. But as you can imagine, like if I don't have this in a list somewhere, I have to work my way backwards and to start from 0 and 1 as the base case and work my way up to, well, what is the 19th number? So that there is a loop there that has to occur. And so we're going to do the loop method here first in this example, and then once we talk recursion, we'll come back, and our final example of the day will be discussing that. So here is some code, and it's more complicated maybe than it needs to be, but again, the whole point of this is a review and just to get used to parameter passing and local variables and all of this other stuff. So this is our first example that actually looks at local variables being used. So I can see I have one parameter getting passed into my function. It's n. And then I have int a, int b, int I, int c. I actually have 4 separate local variables that I'm going to be using throughout this function. And the main's job is just to print out Fibonacci 19. I already have that down here. Push 19 onto the stack, call Fibonacci, call write-int, and I believe, what was it, 4181 should print out of this thing. And I can already prove with my code that it does because there it is, 4181. So now just a matter of talking through it. So here's my main function, and here is something that I want to translate. Say, take away the main. I want to translate this function into pure C++ code. And you can see I've already done it. I already have this. If you've already read through this before you watch the video, you know where this is going. So let's just take a look again. Oops, here is the main. Should probably make that bigger, but not right now. And so then the code itself, oh my goodness. Okay, so again, I actually went ahead and massaged this down and changed things around. Like if I just, without even thinking, right, could you write a Fibonacci sequence in assembly language without any prep work, right? Like, could you just make it work? And the answer is probably no. Like, as much as I got it working, and I got it working on the first try, it was because I wrote it out in C++, reduced it down, because I knew that prep work would save me a ton of trouble on the back end. If something went wrong, I'm spending hours trying to fix a tiny little problem, when if I just wrote out my function in 10 minutes or however long it took me, I could, basically have some insurance that I'm not going to have that happen to me. And sure, things can still go wrong, but if you know how you're supposed to be solving the problem ahead of time, it's much easier to go ahead and try to actually solve the problem. So I went ahead, and since I talked about this being a parameter and these being local variables, understanding how the stack, like I said, the parameter passing would be EBP plus 8, right? Because that's the only parameter on the stack, and it's going to be stored at EBP plus 8. But then I also am going to set up 4 variables here in the local registry, in the stack. So I'm going to have EBP minus 4, and EBP minus 8, and EBP minus 12, and EBP minus 16. And I have to keep track of who's who, because that's all I know is minus 4, minus 8, minus 12, minus 16. Well, what if A was minus 4? What if B was minus 8, and I was minus 12, and C was minus 16? So you can see what I did. I basically just went ahead and, for the most part, just changed up and just changed the names of the variables to accommodate so that the translation would be much more smooth. So my n became plus 8. So I just basically did a global replace and just say anytime I see n, replace it with plus 8. So I see it in 4 places here, at least 4 places here, plus 8. Yep, that's it. I only needed those 4. And then I used minus 4 for A. So anytime I see A, I just replaced it with minus 4. Minus 8 for B. Minus 12. So I actually went ahead here and changed my for loop into a while loop, because the for loop is great for high-level languages, not so great for assembly language, because the for loop kind of throws everything around. So I just basically turned the for loop into a while. Here's the initialization for the I, minus 12. Here's the conditional. Here's the incrementing, and I just turned the for into a while. But everything else the same, and here's my C value, which is my other temporary which is at EBP minus 16. So everything matches up here. As you're expecting, I'm going to return minus 8. So like I said, here is all the code. And let's see if I can bring it down. Can I get it all on one page here? Let's see what I can do. One more time. Let's see. There we go. All right, so all of that, can you see that? As long as I get my big bald head out of the way. Okay, let's see what I can do for you guys. Or I could just, let's see. Oh, fancy. Look at me moving myself over like that. Okay, so what am I trying to do? And since I know this, and I got this working in C++, and I got my answer, 4181, and it's perfectly working fine, now it's just a matter of translating it, and some of it is line for line. Not always. If statements and loops, not always true. But a lot of times you can just kind of just take this now that I have it in a very simple, straightforward manner, and just basically just do a one-for-one translation. And so I have the parameter passed, so I do need the push and the move, and I need the pop and the return. The return is 4 because there's only one parameter. But then now you see this is new here, the sub ESP comma 16. And why is there a 16 there? Because remember, there's 4 local variables in this function, and every one of them needs 4 bytes of storage. So I need to push that pointer, push the the top of the stack, give it 16 more bytes, and now I have that space set aside so nothing can go wrong with that. I just have to remember what's what, and I did because I'm taking care of this here. And for every sub ESP comma 16, I got to do an add over here on the back end. And so sub 16, add 16, push EBP, pop EBP, and then the return 4 to take the parameter off the stack. Everybody's happy. The stack is wound and unwound. So far, so good. And now we have to just go in, and you can see there's some substantial work to make this work. And again, it's not the best solution, but it's just a solution to basically kind of push you through and understand all the little details here. So so let's just kind of go through. So if plus 8 is equal to 0, return 0. So, okay, compare EBP plus 8 to 0. And so now if it's equal, go to the 0 case and say, okay, put 0 into the EAX register because the return of 0, whatever my return value is going to be put in the EAX register. So I'm going to put a 0 into EAX and then jump to done. And then I'm done because, I'm done. I need to unwind the stack. So I say many students over the course of my grading, over every term, have multiple return statements, and I'm definitely like, that's definitely not a good thing to have, and it's exactly for this reason. You're not going to want to put all this information in 2 or 3 or 6 different places about adds and pops and returns and all this stuff. Like, it's just too much. So you need to, this is where the idea of the one in, one out principle when it comes to, functions and things like that, this is where it all comes from. It's just because back in the old days, it was a pain in the ass to have to, if you had more than one returns, just to make sure everything unwound correctly. Modern languages can handle it just fine, but we don't. Our brains and all of this too, it just takes a lot more work. And so if we can, we can get ourselves to one out, all the better. And that's what I did here. If I find a 0, I set my 0, I come around, I set to done, and I get out. And the same thing comes here. If that falls through and it's not a 0, basically that's the else case, and I go, well, how about a 1? And it's the same thing. Okay, I'll go to the 1 case, set it to 1, jump to done, and fall through and unwind, and I'm done. So that handles the 2 base cases, if you want to think of it that way, because it's just, it's easier just to get those 2 out of the way. And so for everything else then, okay, what have I got? I need to set up 3 local variables. And again, -4, -8, -12, there's my 0, 1, 2. That's my A, my B, my C. Okay, this is why comments would be helpful here too. And so, like just to say, what am I trying to do? I didn't put it in here, but you can see what I'm trying to accomplish because I made the worst slide in the history of mankind. Look at all those arrows, right? So here are my 3 move statements, and now here's my while loop. And remember, a while, or basically a for loop, any kind of loop, is a repeated if statement. So when I get down to here, I go, I need a label to come back to because it's a while. And I'm comparing -12 to +8, and again, you can't directly do it because one of the variables has to be on a register. You can't just do memory versus memory. You can never do that for moves or compares or anything like that. So I move -12 over, which is whatever that is at this point. That's the I, and then +8 is the N, right? So I'm comparing the 2, and I go, well, if it's greater than, then I'm done, because I'll fall through if it's a true statement, but if I'm done, this is false, and the opposite of less than or equal to is greater than. So if this thing comes out greater than, I know I'm down to the 2 or more case. And in this case, whatever is stored at EBP minus 8, that's what I want to return. And I'm saying, like, I'm not talking the logic here. The logic was completed. This is, and I know it works. It's just a matter of following through here. So whatever's at EBP minus 8 needs to be put into the EAX register, and I'm done, which is great. But in the body of the loop is where all the rest of the work goes. And so now it's just a matter of saying, okay, I need to put whatever's at minus 4, I need to add it to whatever's in minus 8, and I got to throw that thing into minus 16. C equals A plus B. That's kind of what I'm doing here. Give me A, give me B, add them together, and put it into C. And so the next is, what is that? A equals B? Something, or B, I'm just kidding. A equals B. And so, yep, it takes a little bit of work down here. So because I can't just do it in one step again, so I have to take B, move it into EAX, and then move that into A. And then the next one, minus 8 equals minus 16, is the same deal. It's this, B equals C or whatever it is. Just going back here. Yep. A equals B, B equals C. Oops. Didn't mean to do that. Sorry, I'm not trying to confuse anybody. So we're just finishing that up here and say, okay, move EBP minus 16, move it to EAX, and then shift that over to minus 8. And so that one is done. And then the final step here, increment whatever's at EBP minus 12, and then do the unconditional jump back, because I said it's always an unconditional jump. And so if you forget this, and like especially if the while or the for loop, it's real easy to forget that it's sitting over here in the for loop. That's why I like changing it into a while loop, so it's screaming at me that I have to remember to put that in. Otherwise, you'll get an infinite loop, and it'll never come out of the deal. So I handled all 3 return cases. I handled all of this code, and it just works. I'm saying the logic is there. I already proved the number comes out 4181. And just to prove, it's like if I want 20, I don't know what the 20th Fibonacci number is, but this tells me it's 6,765. So, it is what it is, right? So let's see. What is number 3? 0, 0, 1, 1, 2, 3. Does 3 get me 3? Nope, 3 gets me 2. So I'm just gonna go, let's see. So let's just, if it's 0, just 0, 0, 1, 1, 2, yeah, 2, duh. 3, 5, 8, 13. I hate that starting from 0 thing, right? So 21, 34. So let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8. The 9th Fibonacci number should come out 34, and it does. And so at this point, I'm pretty confident, as long as I can handle this, as long as the int data type can handle the result of the computation, we're all good to go. And it's pretty fast, all things considered. There's a lot of D-word pointers here, but it's pretty fast considering it's using a loop versus the recursive structure we're going to do later on. Okay, cool. So we're done with these examples. We're ready to move on to recursion. So recursion is one of those things, you either get it or you don't. And then, oh man, some of these recursive calls that you can do, but we need recursion for a few things, especially like binary trees and things like that. Like we have to have the idea of recursion. And so a lot of these examples, like they're not the best reasons to use recursion, but they get the point across and they're simple enough, like factorials and Fibonacci. We understand how those things work, like binary search as well. If you know how those kind of activities work, how these topics work, then it's not a huge stretch to see how you can make that thing work using a recursive algorithm instead of an iterative algorithm. But they say no matter, a lot of these things, especially in my advanced C++ class, I go through a lot of things. You can see other videos on my feed here on YouTube of like and Queen's problem and just different recursive algorithms for sorting algorithms and things like that. Like we do need this. But a lot of people can say, yeah, how many times have I done this out in the real world? Like, I've used it in people's libraries, but I've probably very rarely ever gone and done my own recursive work. So here, in this case, what is recursion but a function that calls itself over and over and over again, and there has to be a base case to get me out, because if a function calls a function, calls a function, calls a function, if there's nothing to stop this thing from going, that is not an infinite loop, that's a stack overflow, because as you can see everything we've been doing, I'm throwing information onto the stack every time I call a function. So, and your computer only has a finite amount of RAM, even though it feels like an infinite amount sometimes, it only has a finite, so if I keep piling it on and I never get it away, eventually it's going to break, and eventually my program is going to crash. I'm going to get a stack overflow. So the computer knows no difference when it comes to what function is being called. It just knows that it's calling a function. It doesn't know it's calling itself. It doesn't know. It just doesn't care. And so all of this mind meltiness of all the recursive algorithms and all the things that we need to do, it just comes down to, like our brains can't handle it, or can handle it up to a certain point. Like the Tower of Hanoi problem, I do not understand. I call it Tower of Hanoiing, because it's just, I get what's going on, but I can't get what's going on under the hood when it comes to that. And so you can see, good for you if you completely understand what's happening with all of these recursive algorithms. But if you don't, like I said, don't feel bad about it. Definitely, not everybody hits everything. Kind of like 3D puzzles. Sometimes you see them, sometimes you don't. And so let's move on here. And so I have a function to recursively calculate the sum from 1 to n. So like if I put a 5 in here, I should get 15, because 1 plus 2 plus 3 plus 4 plus 5 gets me 15. And so of course the reality is, like, the best way of solving this problem is to turn this in, and instead of using any kind of loop structure at all, is just do n times n plus 1 quantity divided by 2, and you get the result. But again, that's just beside the point here, just explaining how this all works. So we're going to see in my final example that a lot of this stuff isn't always, you can't always be as suave and cool and just use registers. A lot of times you have to use variables, to like local variables sitting under the hood inside of your stack frame, so that everything is maintained correctly as you're recursively coming and going and moving around and making sure all the values are correctly in place. If you're going to be blowing out registers with every single call, like, there's no way to unwind that. That's why a lot of times you have to add extra information to the call stack to make this work. But in this example, so here I do have working code and it prints out 15. This just shows that this does work. And so here, let me just go ahead and fire up this, and let's just kind of take a quick look. And so just for the sake of keeping you from many types of boredom, let me just use 4 instead of 5. So we should get a 10 out of this when I'm done. So I'm going to put a 4 into the ECX register. I'm going to put a 0 into the EAX register. We're going to kind of hand go through this, and I'm going to call calcsum. And we're not going to worry about the calls to things. We're not going to worry about the pushes and the pops or anything like that. So I guess I don't need the call stack for this problem. But let's just see what's going on here. And when I call this function, just say, like, where am I? I guess, where am I going to return to? I guess I could just say I'm going to return to main. If anything here, so this is when I'm calling calcsum, where am I going to return to? I'm going to return to the line of code main to write. I guess I could say the address of the write int. Like, where would I return to when it's all said and done? Let me just make this a little, oops. Make this a little bigger. There we go. So then now that is on the stack, and let's start. Okay, compare ECX to 0. If they're equal, or if it's 0, I guess in this case I like, maybe Z isn't the right one. You could use JE. They're the exact same, but it reads easier, I think, if you use JE for jump if equal, because if EAX is equal to 0, but it's not, so I fall through. So I take whatever's in ECX and I add it to EAX. Done. All right. I decrement ECX, make it a 3, and then I call calcsum. And so what is the next line of code? I go, the next line of code is a return. Okay, so that's what, and now I'm into the next winding up of the call stack here, and the next call to calcsum, right? Because I'm calling that, putting the address on, and go into town and say, hey, ECX, are you 0? Nope. So I fall through and I go, hey, let's take whatever's in here, add it into here. 4 plus 3 is 7. Decrement ECX, and then put the address in. So the next line of code will just be a return. And so now do it again and go compare ECX to 0. Nope, not yet. Add whatever's in here to EAX. I got my 9. Decrement. And then basically another ret goes on the stack. And now call again. And now, this is the tricky part. Like, I'm 4 levels in right now, right? So, like, it's very tricky with a debugger to see where you are. I wish I wish you could pop up multiple versions of the same function so you could see that you're in like the 4th iteration right now. You could see it from the call stack, but you can't see it. If I didn't have this written down, you wouldn't be able to visualize this. And the call stack in the debugger a lot of times does not help in the same way you might want to visually see this. So coming back around one more time, hopefully I remembered where I was. Okay, well, is this 0 yet? Nope, fall through, take whatever's in here, add it to it, decrement u by 1, and then say, okay, here's a ret. And now I call one more time, and I go, hey, okay, you're 0 now. Hey, you're equal. Let's go to L2. So the recursion is done, because you can see that the EAX register is holding the correct value, the 10 that we're expecting to see. So now it's just a matter of unwinding the loop. So this return returns, it's not any of these return, I guess it is this return. I return back. And so what do I return back to? I return back to the last call to call calcsum, which now is done, which falls through, which is this return value, which returns me back to the previous calcsum, which falls through, and now it's this return, which then comes back again to calcsum, which does this return. And then there's one more here, since we did this 4 or 5 times. And now we'll do it one more time. You got fall through here again, because I'm done with that function call now. And I return, but what do I return to? I return back to main. And now when I get to main, I call write-int. It'll print the 10, because that's the value it should print. So mind you, say, like, my rule of thumb is always, when I call these functions, is to make sure that every register is put back to what it was. So just say the EAX register is correct, but just so you are aware, like you're saying, like you would put a little note here that the ECX register is always reduced to 0 by this function call. And it wouldn't be the easiest thing in the world. You'd have to have you could put a push and a pop. And so the ECX register would not be put back to what it would be put back every single time. But so in a recursive function, it's a lot of pushes and pops, and a lot of times with recursive functions, you're calling this function hundreds, tens, or hundreds of times, which is just slowing things down. So there are ways around this. Maybe put a push, like maybe have a whatever. Who cares? But I'm saying, like, there are ways to get around this. But for me, this isn't 100% complete yet. You get the right answer, but you still have it's a quick and dirty solution. The next step would be to make this foolproof so that EAX is modified, nothing else is. But this is what I want to go for. This is what recursion is, the basics of this. So let's take a look. We only have a few more slides. Let's see what else we got going here. Next up, another one of our favorite kind of functions, the factorial. Factorial is kind of like a summation, but instead of summing things up, you're multiplying everything together. So instead of, like 1 plus 2 plus 3 plus 4 plus 5, factorial, 5 factorial is 1 times 2 times 3 times 4 times 5. And usually, just to make things easy, we start from the end value and work our way backwards. So I said, we all know factorials, right? I mean, there really is no need, should be no need to discuss this. You could just use a for loop. And the interesting thing is factorials grow so quickly when it comes to, just the way things rise when it comes to 2 times 3 times 4 times 5. So I believe for a 32-bit int, I believe you can only hold up to 12 factorial. And so it gets a little tricky. Like, you're going to have to use, if you want to have large factorials, you're going to have to figure out a way to make that work a little differently. So here is a recursive function to handle this, because it's 7 times 6 times 5 times 4 times 3 for 7 factorial. So I'm saying, like, if n is 0, return a 1. And that's just one of the things that just mathematicians understand, that 0 factorial and 1 factorial are 1. So it's just a matter then, if n is equal to 0, return a 1. And so everything else just comes down to, like, okay, hey, Brad, what's 7 factorial? And I go, nope, I don't know what 7 factorial is, but I could tell you that it's 7 times 6 factorial. And then you can see where this is going. And then you're like, well, I don't know what 6 factorial is, but I know it's 6 times 5 factorial. So essentially, you take 7 factorial, and then it works down into basically being 7 times 6 times 5 times 4 times 3 times 2 times 1. And once you get to the end and you're like, okay, I returned the 1, everything starts unwinding, and all the multiplications kind of happen in like a chain reaction. And then when you finally come back, that final return holds the correct value for the factorial that you're looking for. And so you have recursive, so you're recursively calling, and then as you're unrecursing, as you're unwinding the stack, you end up with 5 factorial being the 120. But in this case, like this, to make this thing work, I need to store the variable I need to store that n. Well, I guess I don't have to store the n, but for the other one, I will have to store something. Let's just take a look at the code here. And this is just some example here. And this time around, I actually went ahead, since I used imul, I did the push of EDX and the pop of EDX before everything else. So just understand that this might be a little different than what you've seen if you have the previous lecture notes or anything like that. So this is how the stack would be set up. And so because of the way everything is set up, it takes 16 bytes, because the way I'm doing things, it takes 16 bytes per function call, per stack frame. So that means, it doesn't seem like a lot, but it does add up, especially, if I was, for Fibonacci or whatnot, those, 16 and 16, the way everything branches out, that adds up to a lot of space after a while. But let's take a look, so we're just converting this basically into, I don't have that here. Yep, I have factorial here. So again, since I'm passing a parameter along, I'm just going to be going here and saying, okay, I have my push EBP and I got my move EBP. I've got my pop EBP and my ret4, since it's one parameter getting pushed in. And so again, let's just say this up front, because EDX is blown out, it's the only thing modified that isn't EAX register inside of the entire function. So then I can just go ahead and just push it and pop it. So now the rest of the code is what I care about. So let's just kind of take a look here. Let's just do, I just keep it simple as always, right? Let's just do 4 factorial. So if I push a 4 onto the stack, and so 4 gets pushed onto the stack, the address of main gets pushed onto the stack. So what have we got going here? So right, and then so the 4 gets pushed onto the stack, the main, and then the EBP value, right? So like I said, this is the top of the stack, so EBP plus 8 is where the 4 is stored, right? This is all that fun trickiness of, this is the top of the stack, this is where ESP is pointing. So then, and then EBP points there because of the way we set everything up. So then plus 4 plus 8 gets me to the 4. So I compare 4 to 0, and of course it's not, so it's not equal. So yep, I come around and I do some work. So I'm saying, okay, take my 4 and move it into EAX. Okay, so far so good here. Take 4, move it into EAX, decrement it, push it onto the stack, call factorial. And so let's see, let's call factorial, and let's just say, what is the next line of code that comes after it? We'll say the address of the imul. Okay, so it's going to do that work now. It's calling that function. And we're not doing the imul yet because we're now physically calling this function. And so the next thing I do is push EBP onto the stack. And then I push EDX, and let's just not worry about EDX. Let's just kind of let that one fall away. It all works out fine just the same. But again, I'm comparing EAX, I'm comparing EBP plus 8, which is, in this case, it's the 3. Comparing it to 0, it's not equal to 0, coming around, moving the 3 into the EAX register, copying in there, decrementing it, pushing it, calling the function, which returns again the imul, coming back again. So you're going to see this one or two more times, EBP. And so you're like, okay, here I go. So the stack is getting filled, and just like you see here, the stack is getting filled with all this crazy nonsense. So I do the comparison again. So 2 is not 0. So I come around, put the 2 into EAX, decrement it, put it on the stack, call the factorial function again, one more time. And so now put the EBP on the stack, one more time, right? So, and then compare the 1 to 0. It's not 0. Come around, put it into EAX register, subtract 1 off, push it onto the stack, call the factorial, and here you go. Now we can finally start unwinding. Oh goodness, right? So what am I doing here? I'm putting that on here, and I'm calling the function, and I'm putting EBP on here one more time. And now I'm saying, hey, compare EBP plus 8, which is the 0 to 0. Oh, thank goodness, right? So now what happens is that I can, instead of jumping around here, now I'm setting it EAX to 1, and I'm coming around. There's no more recursion. I'm going to done, and I'm popping off the EBP. And again, don't worry about the EDX stuff. I'm popping this off. I'm doing a return plus 4, which kills that. And so now I'm returning back to where the imul is. And now I'm ready to do a multiplication, because that's the next line of code, is falling through that last factorial and coming down to here and saying, oh, okay, whatever's at EBP plus 8, which is a 1, multiply that against whatever's in EAX, and I do. It's now 1 again. 1 times 1 is 1. I fall through. I pop off EBP, put it back. I do a ret 4. And then where am I at again? I'm back to the IMUL again because I fell through another factorial call down to here. And now EBP plus 8 multiplied by EAX. Now it's 2. 2 times 1 is 2. Fall through, pop EBP, ret 4. Now I'm back again in factorial. I'm down in the IMUL again. Take EBP plus 8, multiply it in. There's my 6. 2 times 3. Fall through, kick off EBP, ret 4. Now I'm still, because of I'm still one more time in factorial. And now I fall through one more time. I say, okay, EBP plus 8. 6 times 4 is 24. And now pop, return 4. The stack is completely unwound. I'm back at main. I'm back here at the call write int. 24 is the answer. 1 times 2 times 3 times 4 is 24. So I will print the 24. So that is the recursiveness of the factorial in action. And it is what it is, but this is a perfectly legit working copy of that. And when I get out of this, the EDX register is also returned. So I said previously that in this previous example, the ECX register was not returned. But with this, the push and the pop I have here for EDX, I can guarantee that the only thing that's been modified when I come out of this thing is the EAX register. So our final example here is going to look at Fibonacci for the second time in this half hour, however long this video is. No clue how long I've been going. So if the n value is 0, return 0, because if it's the 0th Fibonacci, return 0. If it's the first Fibonacci, return 1. And this might be a little different than you're used to seeing it, just to kind of push the point along that I do need to maintain, since I'm going to be calling Fibonacci twice, I do need to maintain one of the two values, and I can't maintain it in a register. I can't trust a register since this Fibonacci might call hundreds of times depending on how things are going. And so because of that, I have to set up a local variable inside of my stack frame so that I can maintain that information within my call to the function so that when the other one comes back, I can go ahead and work with it. So what I did, again, I went ahead, since n is the parameter and a is the local variable, I went ahead and I changed the n to plus 8, because just remember again that the parameter starts, if the EBP is here and the memory location for the return function, for the return from the function is here, then plus 8 is going to be where the first parameter can be stored. So this is EBP plus 8, and this will be EBP minus 4. And so you can see that I just went ahead plus 8, plus 8, plus 8, plus 8, plus 8. So there's, oops, sorry, that's everywhere. N. There's 5 n's in here. And then there's 2 spots for the A. And so minus 4 is where you see the other 2 parts. And so now that I have this set up this way, again, maybe it took a little time, but in the end, I did this all without even, I tested it after I got done with it, but I did this all in the PowerPoint without even needing to make sure I was doing it, because I translated every line or every kind of statement here one by one by one in here. So, okay, so what have I got? I have a parameter, so I have to pass in EBP, do the EBP thing, and then it's only one parameter, so I'm returning a 4. Okay, I have one local parameter, one local variable, so I do the sub ESP comma 4, and then I do the add ESP comma 4. So there we go there. And so otherwise now that covers all that other stuff. And surprisingly enough, we're not doing any multiplications or anything in here. And we're not modifying anything but EAX, and we're returning EAX anyway. So no other registers are modified in the process. The RAM is, the plus 8 and the minus 4 is, but once we unwind the stack, we don't care anymore. So this simplifies a lot of what we do. Maybe it feels complicated, especially since we're redoing this recursively, but in the end, adding these local variables simplifies a lot of the programming we do. We're no longer fighting for EAX and EBX, like, oh, now I need to use ESI because I have no room for all these different locations for all these different things. So now what am I doing? Compare here, if D word pointer is equal to 0, jump if not equal to 1 or greater. Okay, so if I basically if jump if not equal is false, that means they're equal. So set EAX to 0, jump to done, unwind and go. And the same goes for ones. Test the +8 against 1, and if it is equal, then put a 1 in there and jumped and done. But otherwise, basically, here is the gist of it. Here is the recursive nature of it all. So I go ahead and I take whatever's at +8, bring it into EAX, decrement it, because I don't want to modify +8, because there's nothing saying, this line of code, EBP, or the +8 minus 1, is trying to tell me that I'm creating a temporary -1. I'm not modifying +8. I'm just taking it and subtracting 1 from it. So I need to store that in a register, and that's what I did. Take whatever's at +8, move it into EAX, decrement it, and then push that onto the stack so that I can call Fibonacci. So this is how I would set up the first call to Fibonacci, and the return value will be in EAX, and that is what gets put into the -4. So that's why I immediately go ahead and say, okay, EAX, move that into D word pointer, EBP -4. So that, all that, 1, 2, 3, 4, 5 lines of code handles this line of code. And this return adds just a tiny little bit, but it's the same basic principle here, where I'm taking the same deal. I'm taking I'm taking +8 right here, and I'm putting that into EAX. I'm subtracting 2 off this time, because that's what I need to do. I push that onto the stack. I call Fibonacci, and whatever returns back would be in the EAX register. And this time around, because I can take whatever was at EBP -4, because that's the variable, that's the local variable from the previous call, and I can add that in to whatever EAX returned, and now EAX holds the return value, fall through, and I can unwind like anybody else, like the 0 or the 1 case. The EAX register holds the correct value. So that is pretty much how that all works out. So I was saying, like, was that 6 lines? 1, 2, 3. No, so I guess still 5 lines of code for each of the 2 calls. It seems like it should be a little bit more based on the fact that you're returning and this and that, but the return is kind of handled by the done label, because as long as EAX is in the correct value, we're unwinding the same no matter what. So that pretty much covers, is the mind-bending world of recursive functions. There's obviously more to it. And in the book, there are plenty more examples, and the world has plenty more examples as well. But I think that covers everything pretty closely up to the current moment here. I will forego the coat this time. That coat is way upstairs, and I am too bogged down with making videos for you guys to go find that thing. But as always, swardb@cud.edu is where I can get you can get in contact with me through email. Send me a comment through the YouTube channel if you don't have that or don't want to send me an email. Don't sit on your questions, especially my students here and those of you watching this. Do not sit on these questions that you have, like, what is he doing? Why are you doing it? Because it all works. It's just a matter of, once you realize what's going on, it's pretty cool stuff. So especially recursion, like I said, I'm not going to do Tower of Hanoi. I'm not going to do all those crazy things. Like, that's up to you. High-level languages, yes, let's not do that in assembly language. So again, thanks for everybody for sticking around. And this might be the last video that I have in the series for this course. So you made it. I hope you do well in the final. Hope you do well. Hope you great, good grade in the class. Especially those in the Lewis program, you get to move on to Lewis, move on to bigger and better things. And I'm proud of you guys for making it through. And thanks, and see you around.